So, thank you very much. Welcome to this talk where we're going to discuss functional programming in LabVIEW. And well, you might say LabVIEW is technically speaking not a functional programming language. And of course you'd be correct, it's not. But then again, neither is JavaScript or Python for that matter. And you can still write very functional style code in these languages. So one of the key strengths of functional programming is that it's supposed to make testing easier. And if you know me, you probably know that testing is something I tend to care quite a bit about. So my idea with this talk is to go on a small excursion into the world of functional programming and see what we can take away from there to apply in LabVIEW, in graphical programming, to make designs better and help us with testing. So, hope this sounds good. Before that, let me just briefly introduce myself. My name is Anton Sundqvist and I run a small consultancy business up here in Finland. I'm an NI integration partner and I do all the typical NI stuff. I recently became a LabVIEW champion, which I'm of course very happy about. And in addition to all consultancy and LabVIEW development, I've been spending a lot of time on the tooling around testing, most notably then LUnit and LMock toolkits, which I've been working quite a lot on. But enough about me, let's discuss programming paradigms. So what is a programming paradigm? And in essence, you could say that it's kind of the mental model we have for computation when we write programs. And something that we are probably all very familiar with is the idea of procedural programming. And in procedural programming, we kind of organize the code into procedures, and we can have procedures call each other. We can use something like variables to share data between the procedures and build up our programs in this way. In LabVIEW, it probably looks more like this, more idiomatic LabVIEW, and this is all fine. This is the good old LabVIEW that we are all very used to and have learned. And it works, but it got some problems when you try to scale it up. And if you need then more flexibility, you might opt for something like object orientation. So that's then another programming paradigm. And in object-oriented programming, what we do is we tend to group all our code into classes. And in the classes, then we of course can have private data and we can have private method. And in this way, we can then of course separate the implementation of the code from the usage of it. So as a user of the class, you don't need to know anything about the implementation if it's well designed. And the other way around, you can change the implementation without affecting the user. So you have this kind of abstraction. But that's not really why we do object orientation. So you could do something very similar with a library and access scoping that really the cornerstone of object-oriented design is the idea of dynamic dispatching or polymorphism in other languages, what it's called in other languages. But anyway, we have the idea that we can have an object which is of a specific type, and we know about the type, but we do not know about the object, and then we can still use the object in the different ways. So when we have code that looks something like this, at edit time we don't know what's going to happen there because it depends on what's coming in on the terminal of this VI here. So we have dynamic dispatching, which should probably be familiar to most of us here. So what about functional programming then? In functional programming, there's a few very important concepts. We have concepts like immutable data, we have pure functions, and higher order functions. In LabVIEW, for us as LabVIEW developers, I think that immutable data and pure functions are the most important ones to understand. And a pure function, this is now a function that doesn't have any side effect. So it's something that you can run anywhere, you can run it as many times you want, and it will always do the same thing. So it's something that's almost mathematical, or it is very mathematical, like a mathematical function. And it could look something like this. We have some inputs to the VI, it does some kind of calculation, and it returns an output. So there's nothing else going on here. We don't fire off rockets, we don't send emails, and we don't access any hardware in any way. And this has some nice perks, because this makes the code very easy to reason about. It will always run the same, give you the same output for some given inputs. So there's no guessing. Everything is completely deterministic in that sense. And we can run it anywhere in a CI server, on a phone. Well, maybe not. But anyway, you get what I mean. And if you then want to summarize functional programming, you might say that, yeah, it means that we then get rid of all the side effects and we only write pure functions. And while that would be nice, it's not really practical because side effects are kind of why we write the programs in the first place. So these are really the core ideas that we want to happen when we run the software. So a more practical approach would then be to say that we want to be very mindful of the side effects, and we want to be very, very deliberate about how we invoke the side effects. And we want to keep the core of the application very, very pure, very functional, and then have the side effects pulled out to the edges of the application. Right. So a lot of the inspiration for this talk came from the book Grokking Simplicity by Eric Normand. It's an excellent book. I would highly recommend it to anyone that's interested in this topic. In this book, the author introduces this concept that a program, any program, can be divided down into 3 different domains. So we have data, we have pure functions, and then we have actions. Data, well, it's pretty clear, I think. It's facts about events. But importantly, in functional programming, data is immutable. So once you have some data, you won't be able to change it ever. It will always stay the same. So in LabVIEW, that would mean by-value stuff going down a wire. That is immutable data in LabVIEW. Data has no behavior, which is quite convenient because it makes testing it more or less trivial. It is what it is. There is no behavior to it, nothing that we can really execute. So that's all nice, but of course we want some kind of behavior. And then we have the next domain here, which is the pure functions. And what characterizes a pure function is that there is no side effect. So this is a function which doesn't cause anything really to happen in the real world, and it doesn't have any implicit inputs. It doesn't really read any global variables or access the file system in any way or something like that. And this makes these kind of functions very easy to test because we can just give them inputs, run them, and see what happens. And we can do this anywhere. Actions then. Well, these are the nasty ones because these are the ones that actually fire off the rockets and configure the oscilloscopes, read the DAC cards, anything like that. And these are important, but they are very, very cumbersome when you want to do testing because you don't really want your rockets to fire off every time you push to GitHub. You don't want the actions to happen on your CI systems, and you want to be able to run your programs without having the hardware connected to verify that it works. Even if you don't care about unit testing, I think it's still very valuable to be able to run a VI with some inputs on the front panels and see what comes out on the other end. So what I want to do now is to try to get as much as possible of the programs out of the actions and into the other domains. And that's what we are going to spend the rest of the talk on discussing. So let's start with data. I think this is kind of self-explanatory. We have a lot of data types in LabVIEW. We have numeric data types and strings and booleans and everything, and we can combine it together to aggregate data types which are more interesting. And any data type that is by value that doesn't use a reference of any kind could be considered immutable in LabVIEW. And as soon as we introduce a reference, then we have something that's out of our control, so to say, because then it depends on what's going on with the reference in other places. So as long as we keep it pure by value, things that goes down a wire in LabVIEW can be considered data. In functional languages, there's a lot of very elaborate, or in functional programming languages, there's a lot of elaborate type systems which you can use to do a lot of the domain modeling. I think in LabVIEW we tend to use objects and stuff like that, and not rely so much on the type system. But with that said, let's moved to the next domain, which was then pure functions. And I think you all probably got what I meant with a pure function. So it's most of these mathematical, logical functions on the block diagram. It's anything that you can run with some inputs and always get the same outputs out of. That doesn't touch any hardware or anything. And these are, of course, very nice. And you can then, of course, combine them to make more advanced functions or even pure functions. And it could look something like this. So you have a sub-VI which you create. But then it's up to you to keep it pure, to not add anything that causes any actions to happen within the sub-VI. And this is kind of a discipline to follow then, to make sure that the thing that we care about doesn't really call any actions. And of course, we can write tests for this very easily. Now comes the interesting bit, the actions. And if you look in the palettes, they are all over, of course. So anything that touches hardware, anything that sends something on a communication bus, anything that does web requests or something like that, anything that has something to do with timing, putting stuff in a queue, using references, accessing the file system, most command line calls are actions. And also if you look at the VIA here in the middle there, the fact that it doesn't have any outputs is a telltale that this has to be an action. Well, else it wouldn't really, we could just remove it, because if it was a pure function without an output, it's just a no-op. So, I would argue, just looking at a lot of LabVIEW code, that most of our LabVIEW applications are actions. And the reason is that any function calling an action is by itself an action, more or less by definition. So this makes it a bit difficult, because we have all of these functions that we want to use, but now we can't place them anywhere. And I would argue that this is really not a domain issue, because actions are in any programming language and they are everywhere. It's more of a design issue, and it's something that we can work with. So let's look at what we can do to improve the situation. So let's look at what we can do to move more of our program. We can't, of course, get rid of the actions, but we want to pull them to the edges, and we want to push as much as possible into calculations, or even better into data. And I want to do this by looking at an example. And I only have 70 minutes left, so it's going to be a very, very simple example. And it looks like this. And now I want you to stretch your imagination a bit and look at this. You probably already figured out that it calculates a sine wave there in the middle somewhere. But imagine that this is now something that we care about. This is the business logic of this application. So what data we output to the DAC board here is what we care about. This is the business logic, and this is the things that we would like to test. Then the fact that we are using DAC-MX is just an implementation detail. It's just boilerplate that comes with the fact that we happen to have an NI DAC board that we use. But the important things that we are really interested in is this calculation here. So how can we test this now? Well, we can try to hook this up to a unit test, and it looks something like this. And what happens then? We don't really have anything that we can compare here, because this just fires off the DAC task, and then we would need to hook up an oscilloscope or something, and that wouldn't really be unit testing anymore. So let's see what we can do about this. And the main idea here is now we try to separate the action from the core logic of the application, from the business logic, which I just said was this calculation bit down here. So we can just refactor the block diagram. We can just pull it apart and get something that looks more like this. So this is exact same code. We have just pulled out the action here, and we pre-compute all the values, and then we output them to the card. And this is something that's kind of functional-ish, because this is often how functional programming languages tend to work. You typically have a planning phase where you build up a data structure, you modify it, filter it, and reduce it, and then you invoke the action in the end. So this gets a bit better, and at least in my mind, this is easier to understand at a glance, because we have the data up here, and then we have everything with DAC-MX down in the bottom. We can take it one step further and pull out some constants and separate them from that calculation, and then we are left with pure function down here. We have the action here down in the middle, and then we have some data coming in. So tiny steps, we have improved it a bit. But what about decoupling now so that we would, because we are still not able to test this. This still invokes DAC-MX, and it will still try to output something to your DAC board. So you couldn't really hook this up to a unit test, which is the end goal I want to achieve. So what we can start to do is to decouple the action from the pure function. And now we have something like this. We have everything in one clump here. We have the business logic and the action intertwined. And this is difficult to test. So we want to pull them apart. And we could do it, I'm gonna show you two ways to do it. We're gonna start by the simple one, and then we're gonna look at a bit more complex way of doing it in a bit. The first one here is quite straightforward. We have the business logic, generate the data structure, and then it will be the purpose of the main application to take this data structure and feed it to the action. So you can imagine that the arrows here are now the source code dependencies. It's not call representing the call chain. And you can imagine that main will become quite imperative. Now main will just call the action, generate the data structure. It will connect the action to the data structure to the action, and orchestrate everything in that kind of way. And in our example, well, we already have a data structure there on the block diagram. We have the double array, which is completely fine in this example. And we can just wrap our domain logic in the sub-VI, and that we can now test. Simple as so. And the key point here is that we can test it. We can run it without invoking DAC-MX by just introducing a sub-VI. This might sound a bit trivial, but you need to take this in the greater context. This is a very simple example. Right. But I promised that I'm going to show you another way to do the same, to achieve the same results. And what we can do then is we can try to pull it apart in this way, that we have the business logic calling into the action. But this doesn't really help us, because now we have still coupled the business logic to the action through the source code dependency here. So it's still not easy to test. So we need to pull out a trick, which I mentioned in the beginning. We need to pull out the IDs from object orientation and use something called dependency inversion. So what we do is we introduce an abstraction barrier here in between. So we can use an interface, and then we can have the business logic call into this interface, and the action is now implementing the interface. So this means now that the business logic will remain a calculation as long as the interface it calls is a calculation. So it's going to be more clear in a bit. But importantly about testing then. So if you want them to test the business logic, which is what we eventually care about, what we can do is we can introduce a test double here, which implements the same interface. So from the perspective of the business logic, it won't know the difference between the test double and the actual action when we execute it. And we could also run it with an abstract interface and it would do nothing. But I mean, we have all the options because of this seam here, this abstraction that we introduce. And the test doubles, there is a toolkit I mentioned in the beginning called LMOC, which we can use to generate those test doubles for us to avoid writing the boilerplate. So let's look at what this would look like if we want to go down this second route now. So we are back where we started. We have this simple example. And now we have a bit more work to do. So this is a bit more complexity that we add, but we gain a lot of flexibility, as we'll see. And we introduced the interface. Let's call it waveform generator because that's what it is. It generates a waveform. It has one method in it to output the waveform, which takes a double array as input on the front panel. And now we can implement it with the DAC bits. So the implementation is trivial. In the constructor here, we just take the parameters we need and store them in the by-value class. And then when we invoke this generate waveform, we have basically just wrapped everything we had on the block diagram here. And now we can refactor the code to use our new class here. So this is just a slight refactoring. It's still doing exactly the same thing. If you flatten that class, it will still be the same code. So we haven't changed anything. But now comes the step where we change it. Now what we can do is we can pull out the action from this code. So what we do is we pull out this DAC constructor here and place it as a control. But importantly, we now use the interface, the abstract interface. So the last picture here, There's no dependencies and to the DAC class, and this code knows nothing about DAC MX or the driver, so you could run it without even having DAC MX installed. And then when you need to run it in production, you would just feed in the object which wraps the DAC driver. So this is the idea of hardware abstraction. It's probably familiar to everyone here. But this is, for me at least, the main reason why I use hardware abstraction is because I'm able to pull out the action, and then I can have a very functional bit of software which I can test and work with that does these actual calculations and figure out what the hardware should do. All good. I mentioned LMOC already, and I want to show you how we can test this because I promised that you can do it already. What you do is you have your interface in your project, you right-click it, you select mock. This will generate a small testable for you. It looks like this. It has a constructor called create. It has an override for the dynamic dispatch VI, and it has this last VI, which is called a when VI, and this we can use then to simulate responses. So if you cared about if you wanted to test how it reacts to different outputs of the dynamic dispatch, you could queue up response return values using the when VIs. But we're not going to look at that now. The generate waveform VI we can use to verify that the proper calls have been made to the mock during testing. So we can write a test like this. And if you haven't seen an LMOC before, this might look a bit odd. But once you get the hang of it, it's very expressive and easy to read. So it reads from left to right. We create the mock. And then the next two VIs needs to be read together. So we should read it as, during this test, we expect one of the following to happen with these exact inputs. So this is called that we declare expectations on the mock. Then we exercise the code and the test, and then we verify. And as long as the exercise bit now did the same code that we declared in the beginning, the verification will just pass, and we will get a passing test. So in this way, we can test it. It's a bit more involved, as I mentioned, to go down this route, but it has some merits to it. So if we look now at the main application, and if you're working with a framework, then replace main with your framework calling into this code. So it's the caller of the code that we have written now. So from that perspective, it will look very different depending on which of these two routes you went down. The first route is this one that we had, and here we just made a sub-VI, and the main will become very imperative. It will need to direct everything through the application. And this is sometimes called the imperative shell functional core. And the main idea is that the core of the application is functional, and then the main is just orchestrating and connecting everything together. It's completely fine, it's very simple, and it works well in many cases. Then we had the other way, which looks completely different, because now main has a very different style. Now the task that main has is not to orchestrate everything. What it does is it just creates the objects, connects them together, and lets them go off and do their thing. So the idea of creating the objects and connecting them together is sometimes called dependency injection, and this is more or less what this main VI now does. It injects the dependencies and lets them do their thing. So it's much more declarative in style if you look at it, because it just tells this is what we're using, this is a call to it, and then it just goes off and does its thing. So it's kind of more high level. And for a big application, this might scale better, but in the end, it's software design, so you will need to make some decisions yourself. I want to make one last example here. So I already mentioned that we gain some flexibility by using the object-oriented route. And to illustrate this, let's look at an example. Let's imagine that we want to log every call we make to this generate waveform VI, which might be a very reasonable thing to do. So if we had the first one here, where do we place the logging? Where do we need to inject it into this, if you can call it an application, it's a single VI. Well, you can't place it in the calculation because that would make it, we already took a lot of effort to make it a pure function, and if we add some logging to it, it's not pure anymore. So the only place we really can put this in here here in the main VI. So we kind of clutter our main VI now with logging functions, and you could of course extend this to other functions you want to add to it. So we are a bit limited in what we can do, but of course this works fine. Now you just need to imagine that this logs something, not care about the implementation details there. The other case we had here is the object-oriented route, and where do we place the logging logic here if we have done something like this? Well, we can't place it in the one that says sign here, which is the business logic, because we already took a lot of effort making that into a pure function for a pure interface coming in here. We can't really put it into the DAC MX class, because then we clutter our hardware driver with logging business, which doesn't really belong there. So let's put it in the middle. And in order to do that, we need to use a slight trick. We need to use something called a decorator or similar. And just to open up how this works, we need to create yet another class, and this is now following the decorator patterns, which means that in the class private data we keep an object or an interface here of this wrapee, and during the constructor we just feed in the incoming wire here and keep it in the private data. And every time we call the dynamic dispatch VI here for this logger, we just forward the call to this wrapee, and we do the logging on top of it. So in this way we can add logging to it without changing anything in the code. And you can imagine that it's pretty easy now to turn the logging on and off. We just need to place a case structure around this, pink constructor here. And then we can, depending on what we choose, we can have it with or without logging. And well, these kind of ideas scales very well with composition and stuff. But with that, a few conclusions to wrap up the talk. What I want you to take away is to be very mindful about what in your code is actions, what is a calculation, and what is data. And try, if you have something that could be a pure function, a calculation, try to pull out the action from that. And as you start doing this, you will realize a lot of value, and the designs will become cleaner over time. So the actions are pulled to the edges of the application, the core, the things that we care about testing, that we care that actually does what we are paid to do. This is pure functional in the middle, in the core. The book I already mentioned, it's a good read if anyone is interested in this topic. I barely scratched the surface here. It's a very big topic and there's a lot of academic texts on it, but this book is very simple to digest and easy to read with good examples, which I think apply very well to LabVIEW. And if you want to look into LMOC, you can find it over here. And with that, thank you.
Yeah, I just, it's not really a question, but, and I know you know this, and I know you only had half an hour, so you skip a little bit about it. But some people love functional globals, and it's very important to know that if you add a functional global or any state in your VI, initialized, shifted, feedback nodes, you basically turn it into an action, and it will be harder to test.
Exactly. Yeah, that's a very good point that I forgot to make. I meant to, but I forgot it. So yeah, that's something that's typically called an implicit input or implicit output, because it's not explicit on the connector pane or so. And anything that accesses some data implicitly makes that VI into an action and makes testing, reasoning, reuse more difficult. So it's a very good point. Thanks for bringing it up, Wiebe.
May I ask such thing? So we never can have a program which is fully, only functional. We never can have program which is okay. We can have very small program which is only procedural. So we can have object-oriented program, but if it is 100% object-oriented, it is stupid. So but can we define in such a way, when we say about functions here in your terminology, can we say, define it in a very easy way? Functions, it is something which can be put in library and you never take care about what happens inside. Does it work?
I wouldn't define it that way. In the term pure function that I used here is just a function that doesn't have any side effects. It's something that takes inputs, does something with that, and then returns an output. So it's data in, data out. I forgot to mention also the data coming in needs to be immutable. You can't have a pure function working on immutable data. That doesn't work. So it needs to be by value coming in, by value going out. That's the only way to write a pure function. And then it might be whatever. So it can be planning, it can be decision making, and it can generate a very complex data structure which you take out of it and then apply, invoke some action with. But the key idea is that there is no side effects whatsoever in a pure function.
Can I ask a question? Yeah, here on the left for you.
Hi.
Hey. So when you go into the, let's say, planning stage and separate it from the actual actions, don't you get into, let's say, performance issues? Because I can imagine that if your data structure is getting more complex and more greater, let's say, bigger, that you get actually into more performance issue. If you look at your very simple example of generating the sign, if the sign becomes very big, of course, you get into more performance issues than if you would program it into the for loop. This is a very simple example, I get it, but I can imagine if you're talking about scaling, it can also have performance issues or hits.
Yeah, no, that's a very good point. And the thing is that I would not preemptively optimize for performance. It's only when I get performance problems that I try to solve them. But having said that, if you have a pure function, there's a lot of tricks you can do to improve the performance. I mean, you can, this is a big rabbit hole we could go down, but there is like tricks you can do with recursion, and then you can do memorization, and you can do all kinds of patterns on top of it. But of course, if you need to generate a big data structure, then that's going to cost you, and you need to consider it. So it's not, I'm not saying that you always should do it. I said that this is an option in order to make it more functional. But of course, it depends on what you are trying to achieve, really.
Okay, thanks.
But great comment, thanks.
Okay, thanks very much, Anton. Any more questions, pick them up in the break, if that's okay.
Of course.
Great stuff.